Hello, everybody. Welcome to the third workshop of this series, The Beauty of Noises. Usually, I guess people don't usually consider noise as something beautiful, but you know, but compared with random, in this context of programming or in this context of creative coding, you will see how noise can be beautiful and how we can use like noise to create visuals that are more natural. So far we've used random, which is completely random, just goes everywhere, and then we've tried using functions like sine function that create a smooth transition, smooth animation, but it's also goes back and forth. But today we'll be learning noises, which help us produce animation that look more natural. Without further ado, let me start sharing my screen and I'll show you a couple of examples. So this is a P5 web editor, which is what we'll be working with in a second. So this is one of the GIF that I picked as as sort of represent this workshop. This is a blob that moves around. So this is something that would be really hard to do with either random or sine function. And there's a couple of other things that I did. This is very similar, but more subtle blob. I've also, sort of combining what we did from last workshop. I did repetition over here and to create some other effects, adding colors, and by repeating and overlapping, there's all this different thing that you can try. And this one, and then if you put things in a grid and changing the directions, changing the way things overlap, and how big things are, then this is some other sort of way you can use noises. This one, moves around with the noise function. And also those some of those sort of flowery sketches that I created, I also use noise. This I use noise in sort of the contour of each petal. So instead of like a circular or very rigid shape, I was using noises so it has a more natural look. It's essentially just like the blob, except it's once I pick it, it's static, and I just repeat it to create this sort of 3D and flowery look. So enough of the examples. Let's actually start write code to create those. Before that, I'll show you an example of the three that I mentioned: the random, noise, and sine. Let me find that right here. Again, this is another sketch that I created to just demonstrate. So the x-axis is the input. The input just goes from 0 to 400, but the output is sort of the height. As you can see, the first one is random. Essentially, random it just goes up and down. It's just any location, any color. The last one is sine function, which has this sine wave that goes up and down. And then the noise is in the middle, which almost seems like it's alive. Sometimes it goes up, sometimes it goes down. It's kind of unpredictable, but then it also not as sort of choppy as random. And that's what we'll be learning. And since we've used random, and let's see. First, let's start with a circle again, and we'll put the circle at a random location, or more specifically, let's put it at random x-axis. So I will use random for the x-axis. So circle inside of this parenthesis, I'll put random and 400. So that's x-axis, and the y I'll use 200 for the height, and for the y coordinate, and size, it could be any size. So let's run it. So that's random. You can't really find any pattern of where it's going. It's just moves around. And I'm going to give this a title, 26, workshop number 3, random circle. Maybe circle at random x. Yeah. So this is random. That's already something we've learned before. But how? And then what about sign? We can create it. I'm going to. Why is there no duplicate? I'm going to save this and duplicate. And then what about using sign? Then, if we want to use sign function, we can put sign instead of random. I'll type sign, but obviously we do need to, for the inputs, if it's 400, it's going to stay there. So this time I'm going to use frame count, and now the output, as we've learned before, the output is -1 to +1. That's why this is just jiggling a little bit, because it's only moving from 0 to 1, and like -1 to +1. So we want to amplify that by multiplying this, let's see, 200. And now it goes really fast, and I want to move it to, maybe let's slow this down a little bit first. So divided by 50, now it's slower, but I want it to be in the center. Again, because it's -1 to +1, so it's -200 to 200. I'm going to add 200 to this, so that so it moves around the center. I also noticed a question about link to the past class files. Actually, I have been sharing this in the email. I think in the email I mentioned there's a link to all the code we've learned, we've used. Did you not receive that email? Or maybe I'll try to share this again next time. Maybe try to check that email. So if I try to open, and I have different collections, and then one of the first collection I have, I think I need to click on this first, and then there's this collection which has all the files or all the sketches that we use during the workshops. I'll share it in the chat. Yeah, let's get back to this. So that's sign function. So that's how you use a sign function to move left and right. And this provides a smooth movement. And I'm going to add x based on side. And duplicate. So in order to use noise, it's actually very simple to sign. Essentially, noise is another function, and what sign does is when you provide a input, it give you output. Function, the noise function does the same. When you provide this input, noise is going to produce a output. So noise. You see how just simply by changing all the sign that we have, we are already using the noise function. Except you might have noticed that it moves around only on the right side, right part, half of the canvas. That's because noise, the output range for noise is actually from 0 to 1. So the smallest value it's going to produce is 0, the largest is 1. Versus sine, it actually goes from -1 to +1. And that's the reason why it's different. So you can do your math here, just do the calculation, whatever, similar to the sine that we did, or we can also use a map function that we've learned yesterday. I'm going to stop this so it doesn't auto refresh. Map. Again, I'm going to break these into different lines so it's a little better to read. Noise. So the output of the noise is the input for the map, and then from what's the sort of starting minimum and maximum, that's 0 to 1, and what's kind of destination, minimum to maximum, we want it to be 0 to 400, which is the entire canvas. And now let's run this. Now it should move around from both left and right side. Everyone's following so far? Okay. So that's noise. We already know how to use noise. As basically you provide an input that keeps changing, and then output will change in a smoother manner. And now let's try to use noise. Let's try to combine noise and repetition that we did yesterday. So I'm going to create another sketch. Actually, I'm going to create a complete new sketch, and let's again review the repetition that we did before, which is a for loop. So a for loop the for loop basically looks like this: a for loop, parentheses, and curly braces, and inside of parentheses, we want to put three section. Let I equals to 0. That's the initial state, and I smaller than 400. That's the condition under which the for loop continues, and I++. That's what happens after each iteration. So now we have the I, and I'm going to use I for the y-axis. And circle X, I'm going to use 200, or as we've learned before, width divided by 2. So that's half of the width. And then for the height, I'm going to use I, and for the size, I'll use 50 for now. So far, just a review of the same thing that we did before. And this time, we will keep using I as the input, and we'll use the output for the X position. So instead of width divided by 2, I like to use, maybe I'll start with sine, just like we did before. Start with sine. If I use sine as input, if I use a sine function, again, I'm going to break this into different line. So sine goes -1 to +1. I'll use a map function. map this to from -1, +1 to 0 to 400. And that's, again, because I changes too fast, I'm going to slow it down by dividing it to 50. So that's fine. And if I don't, if this looks too much to me, instead of 0 to 400, I can type something like 100 to 300. So it sort of stay in the middle. Yeah. So that's sine. And again, I'm going to give it a name. So workshop number 3. And what the repetition with sine. So that's sine. If I save this and duplicate, and now again we can change sine to noise, and instead of -1, I'll use 0 because that's the output range for noise. And now we have circles based on noise instead of sine. So that's that. And then we can change the input. Instead of 50, if it's 500, let's see what happens. This is almost straight. What about 100? Basically add the input, slows down, then the output also is smoother, but also sort of less changes in the output. So that's one way that we can adjust sort of the characteristic of the output. That's by simply changing the input, like how fast input changes. And one thing to notice, by the way, is that every time you refresh, you are going to see a different sort of path. That's because noise function. So this is where it's somewhat similar to random. So every time you run your sketch, it creates a new noise pattern. So it doesn't stay the same. Yeah. However, within each sort of instance, like once you click run, the noise is not gonna switch to something else unless you explicitly, changing the input. Yeah. So sometimes it might be useful for us to keep the same noise. Like if you want to keep a specific pattern, what we can do is to specify something called a noise seed. So essentially, the noises are different because a different seed is provided. As long as you have the same seed, you are going to have the exact same noise pattern. And seed essentially is just a number. So you can use 0, you can use 100, you can use 10,000. They're just a number. But if we are using the same seed, for instance, if all of us put 0, and assuming the rest of all the code, you write the exact same thing, then we're going to have exact same noise. And that can be, so even if I refresh, it's going to stay as the same. So that in itself can actually be a very powerful tool. So just with that single number, you can have, like, even if it might seem to be a very complicated pattern, but you are really just controlling that pattern with just that one number. As long as the rest of the code is the same, just by changing that number, you create a complete new path or complete new pattern. So that's 0, and for instance, if I use 2, then it's a different one, and 100. try a couple of different ones. Yeah. So that's noise seed. That's if you want to make sure that your noise stays the same. With noise, and now let's try to animate this. Duplicate, and if you like to animate, there are a couple ways that you can do it. One way is to simply change the input. So if you add frame count to the input, because the input is going to change, then the output is also going to change. And as always, whenever we use frame count directly, it's super fast. So we can slow it down by dividing frame count to a certain number. You see how now it's much slower. But one thing you might notice is this type of animation, it seems like the noise, the whole thing is moving up. And that's because the change, as we are increasing the number, everything sort of changes at the same time. So essentially, we are just shifting the noise, shifting this pattern by a little bit. But there's also a different way to change noise, to animate noise. That is to add a comma. So what we are doing here is to provide two different inputs. So when we have two different inputs, the whole thing moves, the whole thing changes. And let me try to illustrate why this is the case. And let me first find my whiteboard. Where's my whiteboard? Right here. Oh, oops. So this is the whiteboard. So as we've talked about, the sine wave looks like this. So whenever you pick input, let's say I choose input here, this is where I choose, then this is your output. The output you get is the y. And then if I pick input here, maybe it doesn't make sense. Let me try to draw a different one. And let's say if I pick input here, then the output is sort of the y. And if I pick input like this here, then this is going to be the output. So here, this is going to be 1. This is going to be -1. And that's the reason why we're talking about, like, we want to slow down the input. So if the input is slower, then the output changes also slower. If your input jumps from here to here, then it's a very drastic change. And now for the noise, I'll try my best to emulate noise. For the noise, similarly, if you change input, it produces a different output at a different location. So what happens with the first version, if we simply add frame count, is earlier, with what noise does here, what we are doing with the circle and for loop is we're essentially drawing a section of the noise. That's how we get that pattern. If you're simply adding the input by 1, then do I have other colors? Yeah. If we're simply moving the whole thing like this, what happens is the first circle moves from this location to the other location, and then the second circle move from there to here. So the whole thing is shifted, and that's why if we simply add frame count, the whole thing is just shifting. That's all what it's doing. However, the noise, now we are just talking about 1D noise, the one-dimensional noise. Noise can also be two-dimensional. So in this case, you have one input and then give you output, as simple as that. However, we can also have two-dimensional noise. So two-dimensional noise would be something like this. So you have, it's almost like you have a grid. I mean, it's not exactly a grid, but just for the sake of this explanation, it's as if it's a grid. And then your input, this time your input is not just a single number. Your input is sort of the axis that, you know, you have both x and y, both x and y is your input. So x and y. And now imagine there are different darkness, different sort of darkness on inside of each sort of tile or each cell. And when you have an input, let's say 1 and 2, so 1 and 2, it's going to find that tile and retrieve the darkness of that tile. So why do we have the darkness? That's sort of the magic of the algorithm, this noise algorithm. The noise algorithm, using certain some mathematical computation, it calculates what's the value for each cell is to produce that smooth animation or smooth transition. Then all you are doing is providing an input, which is the position where you want to retrieve this data. So let's say 1, sorry, that's not 1, 2. That's about 2, 2, yeah. So let's say, yeah, if you want to get the value 2, 2, or maybe you want the 3 and 2, which is here, then whenever you provide that input, it gives you the output. So now back to this. And let's actually move this back to static for a second. So this is static. One way we did is to plus 1, plus 1, plus 1. So it moves, maybe that's a little bit too drastic. So let's slow it down. So minus 2, plus 0.2, 0.3, 0.4. You see how it slowly changes to the up. Or we have this other option, which is to add additional input. So x and y, so we're providing a new axis. So 0 and 1. Again, I think that was too big a change. So 0.1, 0.2. So it's like shifting the whole thing in that 2D space. Yeah. So that's the two different way to animate this. With noise animated. And that's noise. So now let's just make it a little more interesting by adding color. So adding color and also just changing sizes. So let's just go a little bit further with this sketch. So frame count 50. So first, let's try to add noise to the size, which is the last value, like the diameter. I'll just copy this and paste it over here. I hope it's still readable. Maybe I'll make this bigger for now, so it's a little more readable. So map, and I might have missed a parenthesis. Yeah, I missed a parenthesis. So now both the x-axis and I think I didn't copy the whole thing. I'm trying to copy it. Yeah, we do need the whole thing. So this time, I'm still using the same noise function, but instead of 100 to 300, because this is the diameter of the circle, maybe I want something around 10 to 100. And let's see how this looks. Yeah. So the whole thing, the size changes. Maybe if you want the size change to be more drastic, you can make this a little bit bigger. Yeah. And you might have noticed, the size, like the sort of blobbish thing or the circle only increase size on the right side. It seems like that left side is smoother and right side is where where the single circle changes sizes. That's because we are using the exact same noise function for both the position and the size, so they are sort of in sync. As we've done before, whenever you put two things out of sync, that's where it can be a little more interesting. So now it's completely matches. If that's the effect you want, that's totally fine. Or we can just put a different number here. So now sometimes it seems like it's moved to the left and sometimes to the right. You can also use a different speed. Make it even faster. So now the animation, the movement is slow, but the size is fast. So let's make it more obvious. So now the movement is very slow, but the size is very fast. The size changes very fast. So let's try to swap that. So now the movement is fast, but the size change becomes slower. So again, just by changing, different combination of those changes, we can get very interesting results. I'm going to go with like a slower change. Maybe about 50. That looks about right to me. And now we can add a color. So I think I should come up with this animated X and diameter. Now I'm going to duplicate this again and add color. Fill. And this would be the same as we did before with the sine function, I divided by a certain number, and sine is -1 to +1. I want it to be 0 to 255, and I'll copy and paste this R and then G and B and run this. It's the same chain, so it's from white to black, and I'll change this to some other numbers. That's where it becomes colorful, and I'm also going to remove the stroke so we can see those colors. And you can adjust the color by adjusting some of these numbers. So you can have just again, playing with those colors, you can have a lot of different combinations. And remember that we always have the noise seed that we can change that produce like a different pattern each time if you use a different seed. But this is also an example of how noise seed is very powerful. So the whole thing seems like a very random, but every time you play this, it's going to be the exact same animation. even though, and that's something very different from random. And actually, for random, there's also something called random seed that can produce the same sequence of random results. So in that sense, random function actually does not produce like a truly random value. It's also based on the seed, but it's appeared to be random for us, because at the end of the day, it's still some kind of a mathematical equation that that you provide an input and then it gives output. It's just that the math is designed in a way that the output appears to be random. Any questions so far? Oh, good. Yeah. So this is with color. Clear with color. And now let's try to grid a grid. Yeah, let's grid a grid. Again, this is be a review of what we've learned yesterday, but we are going to apply noise function to it. So I'm going to start a complete new sketch. We're going to call it workshop number 3, grid. And do people still remember how to create a grid? No? So let's first define the number of columns. I'll start with 10, the number of rows, 10. Yes, exactly, nested loops. So we want to have one loop instead of another. And then we want to know the width and height. Tile width is width divided by columns. Let tile height equals height divided by rows. And now a for loop. Let's start with row. You can do it either way. Rows start from 0, rows smaller than the number of rows, and row plus plus. And inside we have a column C equals to 0, C smaller than the number of columns, C plus plus, and that's that. And this time let's draw a rectangle. Rectangle. So I'll draw it at the column times tile width. Yep. Columns times tile width. And height is row times tile height. And the width is tile width and height is tile height. There we go. We have a grid. I'll give you a little bit of time for you to type to have your own grid. And let's see what the tidy code will give us. Kind of added a load of the spaces. And I like to, since I have a narrower screen, I'll break this down into multiple lines. And now, how can we use the noise? One way we can use it is to add color. So before the rectangle, I'm going to add a fill. But how am I going to calculate the fill? I'm going to use a noise function. Noise function, what's the input? Let's start with just column. So I'll put input as a C. Notice how it turns almost black. That's because the maximum output of noise is 1. In this case, fill 1, that's like a very, very dark gray. So we need to map this. Map the noise function from 0 to 1 to 0 to 250. Now we have a noise. So every time we run this, it's different pattern. But it's utilizing this noise to produce a color for each column. And I'm going to increase the number of columns and number of rows, so it's a little bit easier to see the noise. Yeah. And for instance, if you think the noise, like if you want the noise transition to be a little bit smoother, then you can slow down the C. Again, slow down the changes of C by dividing it by a number. Now you see it's almost like a gradient. Every time you refresh, maybe that's a little too much, so maybe 10. That's yeah, now that looks like noise. Or that's like the effect that we're looking for. Is everyone able to get to this step, or do you need a little more time? Let me know if you need a little more time. I just want to make sure people are following along. I hope, by the way, I hope everybody is, typing and as the workshop goes, because if you're really just watching it, it's just impossible to absorb all this information. You have to really do it yourself. I'll give you a few more seconds to type all this. And, so as we're waiting, I'm going to go through the code again as sort of a review. Inside of a setup, as always, we have created canvas that creates this canvas 400 by 400 pixels. And inside of a draw, we start with background, which draw the initial background. In this case, it's not even useful because the circle, the rectangle that we're drawing is covering the background, so the background is pretty much useless over there. And then we define the number of columns, the number of rows, and then based on the number of columns and number of rows, we calculate the width and height for each tile of the grid. And then we have 2 for loops. The first for loop is for each row, and inside of each row, we have the for loop for each column. And then for each column, we draw a rectangle, which again, based on the column number and row number, you calculate the width and height for the rectangle. And you already know the width and height, calculate the X and Y for the rectangle, and you already know the width and height that's already calculated. And for the fill, we are using a noise function that's mapped to 0 to 255 to give us this gradient. this to give this sort of different darkness of the tile. So that's one. That's only with the C, only with the column. We can also add rows in here, and as we mentioned, you can provide two different input. And actually, with the noise function, I believe you can provide up to three inputs. And let's just double check. You can always go to the reference to know exactly what the function does. So the noise return the perlin-noise value. Perlin is the person who invented this algorithm, and it produced a number that's was invented by Ken Perlin in 1980s. And so yes, it takes up to three input. So what you're providing is the coordinates in the so-called the noise space. So once you provide a noise seed, or without the noise seed, is sort of randomly pick a noise seed, and once we have that seed, that noise, all the noises before you use it, it's already calculated. The only thing that you need to do is provide the X, Y, and Z. That's where you want to access that noise value, and then this function spits out the value that you need. Here we go. So we have the C divided by 10. Now we can add rho divided by 10. Now you see it's almost like a cloud or some kind of pattern that's different every time. Now we have the two dimensions, the columns and rows. We can add the third dimension by adding a frame count to animate this, so the whole thing will move. So it's kind of, we are moving in the third axis in the noise space. So noise already has two inputs. I'm going to add a third input, which is frame count. You know what's going to happen. It's going to move really, really fast, divided by 50. Now it starts to have this this natural look that we are going for. And obviously right now I'm using it for the color. You can use for a lot of different things to really use to simulate a lot of things in nature. Like if you want to simulate clouds, or maybe you can use to simulate water, a lot of different things. And if you Google perlin-noise, you'll find that perlin-noise is developed by Ken Perlin in 1983. And back then, in movies, the kind of computer-generated image is very sort of machine-like, because it's generated by code. So Ken Perlin didn't like this, and he wanted to, he came up with this algorithm to produce a more natural-looking texture, or computer imagery. And he even was awarded Academy Award for technical achievement. So even if you just work with the code, one day maybe you will come up with the next algorithm that that wins a Academy Award. So yeah, that would and do let me know if you get that one day. So that's what we have with the color and the noise. So now let's try something different. we've done color, we can also use noise to change, let's say, size. So instead of tile width, one thing I like about the output of the noise is that because it's 0 to 1, essentially you can use this, you can use noise as a factor, as in you can just multiply any value by that noise, then the noise function is going to, change that in a way that it's not going to be smaller than 0, it's not going to be larger than the original value. So in the tile width and tile height, you can simply, I'm going to make sure that I'm copying the right amount. I can simply, multiply tile width by noise, and then multiply tile height by width. I'm going to make this a little, reduce the number of rows so it's a little easier to see the size changes. And this, this already starts to resemble some of the sketches that I've shown earlier. And this, in this case, the noise changes, sort of the rectangle always sort of attached to the top left corner, because right now we are drawing those rectangles based on the top left corner. If you don't like that, if you want it to be centered, then we can change the rect mode as we did yesterday. Let me actually save this. Grid noise, grid of rectangles animated with noise. And I'm actually going to step back a couple of times. I think maybe even here. So not stick. So grid of rectangles colored with noise. This is just so that you can reference to this. And then I'm going to duplicate and I'll remove the size change. So now it's just the animation. And so this time it's animated with noise. And then finally, we get to where we are right now. And that's going to be animated with noise. Dimensions animated with noise. That's the one we are right now. And finally, duplicate. And now let's try to move the rectangles to the center. So before we draw a rectangle, we want to change rect mode to center. It's that easy, but now everything is shifted to the top left as it happened yesterday. So we are going to need to adjust to move everything to the right and bottom a little bit, because now if you look at the X value, the first one, C equal to 0 and R equals to 0. So 0, 0, that's going to be top left, but that's not what you want, that's not where you want the rectangle to be. You want it to be center. So it needs to be 0, 0, and then move to the right and down a little bit. You can either add half of the tile width, or you can even add 0.5 to your column. Yeah, you want to shift half of the tile. Now it's centered. And now let's try to add some rotation. So this is where we're going to learn something new. So we've used X and Y to specify the position of rectangles. There is actually another way that we can do it. Instead of directly putting, specifying the coordinates inside of a rectangle, the rectangle function, we can also use something called translate. And what translate does is to move everything afterwards to sort of add offset to the rest, to anything that comes after that. So I'll give you an example. If right now, if we want to move everything to the right, we can add translate. So right after background, I'll add translate 100 and 100. So now everything is shifted to the right and to the right and down for 100 pixel. So that's moving everything there. But what we need here instead of this, so that's what translate does. But we need to do this to all of the rectangles. So instead of specifying the X and Y position, we want to translate to that position. I'm going to copy this. I'm going to translate to that position first. I'll stop this for now. I'll translate to that position. And when I draw, I just simply need to draw as 0, 0. Because now the translate already helped us move to that position. This is going to look a little bit weird right now. That's because every time you're translating, so the translation sort of adds up. So we want to translate to that position for a certain position for each rectangle. There's additional step we need to do, which is push and pop. So we need to add a push and pop at the beginning and at the end. And I'll explain what that is. Centered with translate. Let's look at the code. As we've mentioned, translate moves everything, to a certain offset. But we only want to move one rectangle to there. So everything, the coordinate that we have inside of translate right now is exactly the coordinate that we want the rectangle to be. Without push and pop, after the first rectangle, the second rectangle is going to be, based on the first position. So it's going to further move the whole thing to that location. We don't want that. What push does is to, based on the, what push does essentially is sort of save the current setting, as in save the current sort of location and everything, all the information. So anything that you put between push and pop, it's not going to affect the code that outside it. So right now, so you are basically isolating translate to this, to this area between push and pop. What it means is after pop, if you draw another rectangle, it's going to be the same location. I realize it's starting to get complicated, so I'm going to create a new sketch just to demonstrate this idea. So we'll get back to the sketch, but I'm going to create a new sketch to demonstrate what does push and pop does. So this is a blank canvas. And now let's say I want to draw a circle, 0, 0, and 50. Right now the circle is at the top. how can we move the circle to center? We can either change the location of the circle to center, or we can keep the location of the circle as 0, 0, but we translate to center. Translate 200, 200. So now it's centered. And now, if I want to draw another circle at the center, or maybe let's say if I want to draw another circle at the top left, let's make this slightly smaller so you can see it. So now, obviously, because I already translated 200, 200, now if I draw a circle, it's still going to be based on the 0, 0, the origin. Essentially, what we moved is the origin. So when we move the origin, so the origin is still 200, 200. But let's say if we add more translation, 100, 100, this is actually 300, 300, because we first moved the origin by 200 pixel, 200 pixel, and then after we draw the circle, we move the origin again to 100, 100. But what the push and pop does is to isolate this translation. So in this case, you move the origin to 200 and 200 and draw the circle, and after pop, everything resets. So that's like if I remove this translate forms, that's why if you draw circle 0, 0, it's going back to the top. Essentially, push and pop, make sure that inside you can do whatever you want to do, and outside, like after pop, you reset to the original state. And this way, we can isolate, when we are adjusting those rectangles, for each rectangle, you want to individually specify the X and Y coordinates. So that's why we are doing the push pop for each rectangle. And the reason why we want to do this, use the translate instead of the regular one, is because I wanted to apply rotation. And in order to apply rotation, you have to, or at least one way to do it is to use translate so that you can rotate around that origin. That's one of the simplest way to create a rotation. Without the translate, everything is going to rotate around top left corner, but we want the rectangles to rotate around the center of the rectangle instead of the top left corner of the entire canvas. And I think I can also demonstrate that over here. So workshop 2, maybe translate and rotation. So instead of circle, I'm going to add a rectangle. And again, rect mode, center. So it's centered. Now let's add some rotation. Rotation, essentially just type rotate and maybe half pi. I need to put this after translation. I think, half pi, half pi is like 90 degrees. So it's like, it didn't really do any change. I should probably do like maybe pi divided by 4. So that's 45 degree. Pi divided by 8. Pi divided by 9. Yeah. So essentially now you can rotate. And the rotation happens around the origin. So that's why I wanted to translate. Let's say without translation, let's comment this out. Without translation, and if I put this to the center, for instance, so let's check this again. Right now, this rectangle is at the center, and I'm adding a rotation. So instead of rotating around the rectangle itself, it's rotating around the top left corner, which is origin of the whole canvas. and that's not what we want. And that's the reason why I want to translate to the center first. And one thing that I just said earlier is to comment out. So what does it mean? In programming languages, usually it's very helpful to add some comments. For instance, in the code that I have shared, if you check those code, I actually added a lot of comments. And these comments, in the context of this workshop, the comments is for you so that you can read and understand the code. Sometimes the comments can also be very helpful for yourself when you are writing code, especially when you have a very complicated code. Maybe after a week or maybe after a couple of months, you forget what you're trying to do there. That's why it's useful to have comments. In order to add comments, in JavaScript, we do a double slash, and then you can type anything. So this is background and something like that. And then the comments essentially will be ignored by the program. When your code is run, the comments is ignored because this is comment just for you or for your collaborator or for other people to read. That's really not for the computer to execute. And that's also a helpful feature when we want to temporarily disable some code. For instance, in this case, I want to disable push and pop. That's why I comment them out. So I make them turn them into comments so that they are disabled. They are not affecting the code anymore. And for that, we also have a shortcut, Command/ to turn it on and off, to comment it out, and to uncomment it. So I'm going to move everything back here. And what did I miss here? Background, push, rectangle. Yeah, so now rectangle, instead of 200, 200, I want it to be 0, 0, because we already translated the origin to the center. And before we go back to the other sketch, just to make this sketch a little more fun, we can make the rotation. We can animate the rotation by using frame count. It's a very fast rotation divided by 100. Now it's slower. Maybe that's a little too slow. I want it to be a little faster. And so that's a rotating circle that we have over there. Yeah. Translation rotation. And now let's get back to the sketch we were working with earlier. Right here. So now we can add rotation. I'm going to duplicate. And now after translate, we can add a rotation. First, just to see if this works, I'm going to add a fixed rotation. So everything is sort of slanted. But instead of this, I would like to rotate based on noise. And how much can you rotate? The amount you want to rotate might be from 0 to 330 degrees, or in radian, it's 0 to 2 pi. So I can simply multiply 2 pi by that noise function. And I'll copy and paste the noise over here. So now the circles rotates based on the noise. I understand it's a lot of information. So if you have any questions, let me know. Similarly, you can apply the rotation to a lot of different things. If I make this even bigger, for instance, one thing we didn't learn is for rectangle, there's also a way to specify the corner radius, and we can totally use noise to control that. So I'm going to copy the noise again and add additional input for the rectangle. So that's going to be, maybe I'll use tail width times 0.5. So this almost looks like it's always circle. I think that's probably because the radian is too much, so maybe a little bit smaller. Let's see. Yeah. So now the radius should be different depending on how big, depending on the noise value. And any questions about this? For the last part, we are going to learn how to create a bubble or a blob with noise. But before we move on, just want to make sure everyone was able to understand this. The last item is I'm not sure what exactly you meant. The last one is referring to the corner of the rectangle. So if you go to reference and search rect, you'll find that you can use 4 values or you can use 5 values. The last one is going to be radius of the corner. And you can specify all the radii, each corner. So top left corner, top right corner, bottom right corner, bottom left corner. And if you only provide one, it's going to be applied to the rest, all the corners. So there's a question, why did you multiply noise by 2 pi in the rotation function? So for rotation, I'm going to comment this out for a second. So comment out, so it's no more rotation. And for rotation, let's see what does rotation do. 0 means no rotation. 0.2, a little bit of rotation. 0.5, more rotation, and 6, and so on and so forth, until it's 2 pi, which is about 6 to 8. That's a complete circle, essentially. So 6, maybe a little bit to here. So to finish a complete circle, like maybe let's start from 1. So 0 is this, 1 and move already a lot, and then 2 to the other side, and 3 and 4, all the way until 6. That's when 6 and 6 to 8, or or essentially 2 pi. That's a complete rotation, all 360 degrees. And now I want to use noise to make sure that it just, from 0 to 360 degrees, use a noise, which is somewhere from 0 to 1, use that as a factor to adjust how much you want to rotate. And that's only because I want it to be rotating for the whole range. If that's not what you want, it's totally fine that if for instance, I don't even have to put 2 pi, I can just leave it like this, then it's always going to be rotating somewhere between 0 and 1, which doesn't finish the complete circle. And or you can even do like more, like 5 times 2 pi, then it rotates more than 1 complete circle, moves beyond that. So as the programmer, you really have the control of whatever you want to do, of how much you want to rotate. And by the way, by default, we're using radian, but we can actually, if you prefer working with degrees, you can also change the mode. Let's go back to reference. Okay, okay, refresh. You can see in the mode, there's also angle mode, where by default, it's in radians, but then you can also change the angle mode to degrees, so you can work with 0 to 360. So in that case, I hope that's the only place that I've used angle. So in that case, angle I think it's lowercase angle mode. And if I use degrees, now you see it barely moves because 2 pi, in this case, 2 pi is just 6 degrees. So 360 degrees. So that would be the exact same thing in degrees, if if that's what you prefer to work with. Yeah. And then if you only wanted to rotate half 180 degrees, so it never past half of the rotation. And I'll keep it at 360. I'll translate. I'll add this time rotation. Animate it with noise. And again, I'm going to have both versions for people to learn. So this, I'm going to put 2 pi, and I'll duplicate this and put and paste. So 360, yeah, both the degree. This one, noise, rotations in degrees. Yeah. Okay. If there's no more question, actually, let me check those chat. How you the corners. Okay. So for the corner, let's take a look at the corner. So for corner right now, if I delete this for a second, so if there's 0, there's no, no corner. So the corner is not rounded at all. If there's 1, then it's rounded by 1 pixel. You can barely see it. 1 pixel, 2 pixel, 3 pixel. So this value just adjusts how round you want the corner to be. And more specifically, this value is the number of pixels for the radius of the corner. And what I was trying to do is over here is to use the noise function to apply the corner. I think that the result is not very obvious because there was too much that we are changing. So actually, let me create a new one that focus on corner. So that's a little more obvious. Corners. And I'm going to delete the unrelated stuff. Rotation, I'm not going to rotate this time. And I'm also going to keep the static width and height. Yeah, so now the width and height, maybe I'm even going to keep the same color. Yeah, let's really just focus on the corner. So now, and because the corner is the radius, so of the corner, I mean, this value is the radius. So the maximum value you can have is half of the tile width. Yeah, because if you, in order to have corners on all 4 ends, for each corner, the maximum, you can have a value that's larger than 0.5, but even if you have the corner, the radius is that big, it's still the actual radius is going to be half. Sometimes I think it's probably easier if I just draw that just to further illustrate what the corner is. What word? So this is a rectangle, and this is the corner. So what we meant by the corner radius is that all the corner essentially are part of the circle. If you think of that corner, and this is the center, this is the radius. That's why the biggest corner that you can have, the roundest corner that you can have, is going to be something like oops, I'm not the right spot to draw the circle. The biggest roundest corner you can have is something like this, which means the radius is going to be half of the height. In this case, it's half of the height. Because we had the square, all the shapes we had are squares, the height and width are essentially the same. Basically, the largest corner that you can have is going to be half of the smaller side, either the width or height. That's why I'm doing like a 0.5 over here. So half of the width, and then noise is going to be anywhere from 0 to 1 to adjust how much radius we're changing here. And I hope that explains it. We only have 20 minutes. It's actually a little bit short for the blob. So I think it might take a little bit longer, or hopefully you have, I mean, I do have time, so I will then make sure that I demonstrate all that. So if you don't have time, you have to go at 4, feel free to leave and you can come back and watch the recording. So now let's start a new sketch. That's the last section, and that's also, you know, the sort of the blob that I have demonstrated. In order to create a blob, let's start with a circle. Again, a lot of what we are doing is based on what we've already learned, and we are just adding a little more twist. So let's start with the circle. How do you create a circle? Obviously, you can just draw a circle, but this time, because we want to manipulate, we want this to be a blob, we want the circles to move around, we can't just draw a circle. We have to use different, you know, earlier we used like multiple circles to form like a repetition of circles to form a larger circle. That's one way to do it. And this time we are going to use curves, which is also something covered in the previous workshop. So let's start by writing degrees. So when you think of circle, essentially you're starting from let's say a 0 to all the way to 360, or from 0 to 2 pi. So let I equals to 0, and I'm trying to think which way. Yeah, there are multiple ways to do it. I'm just trying to consider like which way is easier to understand. I think I'll stick with the number of the number first. So I equal to 0, I smaller than a number, like number of in this case number of you can call it joints or vertices. Maybe I'll just keep it simple as set as number, and I plus plus. And obviously we didn't define a number yet, so this is going to give us error that says number is not defined. So we want to define it by typing number equals to a certain number. Let's start with 10. And what we did before was to draw this with a circle. So circle, sine I, cosine I, and then the size of the circle. And for this, times 100 times 100. And in order to make it, so now that we've learned translate, so in order to make sure this thing is centered, there is this easier way to center it, which is to translate everything by width divided by 2 and height divided by 2. So now this is centered. And because I changes just from 0 to 10, which is not actually even, which is not even a distributed in terms of angles. So we want to do that by I divide by number. So now I divide by number is going to start from 0 to all to 1, but we want this to finish. By the way, I think maybe this helps to understand. So it start from, essentially in this case, it started from 0, and then it goes all the way to 1. So over here, this is 1 in the sense of a radian. So for instance, if I 20, it's always start from 0 to 1. If we multiply this by pi, both of them, now it goes all the way from 0 to pi, which is 180 degrees. And it looks a little off because we had 20, so there's like the last one is like, yeah, very close. We'll leave it at 20. And if we want a complete circle, instead of pi, we want this to be 2 pi. 2 pi for both. Now we have a complete circle with the circle that we had. So that's forming a circle with circle. This actually is one way to do it, and let me write this, give it a name. Workshop number 3. Small circles forming a big circle. Yep. And I'm going to comment this out. So instead of circle, we've learned vertices yesterday. So we can use vertex. But in order to use vertex, we have to start with begin shape and end with end shape. So that's before the for loop and after the for loop, because inside of the for loop, we are going to use the same value for vertex. I'm going to copy and paste the values that we have for circle and use that as vertex. So essentially, we are using those points to create a polygon with begin shape and end shape. And make it smaller so it's more obvious where the polygons are. And we can even, instead of putting, let's see. I'll see what's happened when circle. Okay, that's interesting. I draw the circle first. But yeah, we can even leave the circle over there just to give us indication, just for now, give us indication of where each point is. Or you can remove the circle so we only see the polygon. That's up to you. So big circle with vertices. And as I mentioned, if you want to close it, you can close it over here. Close at end of shape, that close the circle. And then, depending on how smooth you want it to be, you can add more. Essentially represent the radius of the circle. Let's say I'll create a new variable called radius, 100, and I'm going to replace 100 with radius. Maybe I'll go over here, radius. So now, if you change it to 200, the radius is 200. If you change this to maybe 10, it's a very small circle. 100, that's a bigger circle. So that's the radius of the circle. So now, in order to, if you want to animate this, or if you want to apply a noise function to this, what we are animating or what we are adjusting essentially the radius. And we can add, but because we want to adjust it for each vertex, that's why we want to put a vertex inside of, we want to put this a noise function inside of a for loop. So radius, maybe I think I can put the radius, maybe just for simplicity's sake, I'll put it directly inside a vertex. So I can simply add a noise function over there inside of a vertex. Big circle, let's duplicate. And noise function times the rest. And what's input? This is actually really important. For now, I'm going to use I, but we will notice that I does not do the job, or it doesn't do it perfectly. So I, and we want this to be applied to both the width and height. Again, I'm going to break both the X and Y. I'm going to break this down to multiple. Yep. So noise X. So it seems like this is already working, and but there's actually a very important part that's missing, which is that the first point and the last point is not going to match. And what can we do here? So maybe 20, something like this. Yep. It's already starting to look like a blob, except that we are using this our sharp edges. So purchases with noise, but we will deal with that later. So right now we already have the noise here. Every time it's different. But in order to achieve that blob effect, instead of vertex, we want to use a curve vertex. You see how now it's round. But because we used for curves, ideally we actually don't want to use closed, because let's use a few more or less. Yeah, you'll see that every time when we generate a curve, there's always a sharp edge, and that's where the curve is automatically closed. So if I remove this close, you'll see that the curve that the circle we generated actually does not, the first and last one does not match. And because of that, if we simply close it by combining it, I think it's because it's changed every time. So I'm going to add a noise seed so it's a little easier to see. So this is the curve. If I'm going to add close, it's simply combining, closing it in a somewhat weird way. Yeah. As I mentioned in the last workshop, the first and last, let me have all the circles. I'm also going to add this to the circle so you can see them. Times. Yeah, there we go. Yeah, so you see how whenever we use curves, some of the vertex is not actually used. I mean, essentially the first and last one, because again, that was used to control the curve. And when you close it, it just abruptly connects all the curves, and that's not smooth. So that's not what we want. And how do we do that? First of all, how can we have a complete circle? Let's step back to the regular vertex instead of close. So basically, the close function is helpful with straight lines, but it's not so helpful with curves. So how do we make sure we close? Going to common out circle again. How do we, and maybe also add a little bit of stroke weight, so it's easier to see. How do we close that ourselves? We are the programmer. We want to make sure that we close it properly in the way we want. The way to do that is to keep going with the number. So the number of the what is it? The number of vertex. We want to add additional one. I realize that I'm going to step back a little bit over here. Let me remove this. So this is essentially what we're doing is we're starting at the bottom. We're starting somewhere around here. Maybe now I can use that zoom feature. Annotate. We're starting here. This is 0 and 1 and 2, 3, 4. I should have had a smaller number. 6, 7, 8, 9. I has to be smaller than 10, so the biggest number is 9. If you want to complete this, then that means the last number has to be 10. And that's the reason why I decided to add 1. So if you add 1, then I is going to start from 0 and go all the way to 10. I'm not sure why I did not complete that 10. Yeah. So this way, it starts from 0 and goes all the way back. And now let's try to change this. So this is with vertices. Circle with vertices. Let's say complete circle with vertices. And duplicate. Now let's see curve vertex. Now it's missing something. And that's because curve vertex require two more, what is it called? The vertex in order to, the first and last one is missed. So that's why we want to add 1 and add another one. Now we have a complete circle. Okay. So let's start with this complete circle. So even just to create a complete circle with a curve, we actually need, so that's 12, that's 13. Yeah, that's we need 13 vertices. Instead of 10, we need 13 vertices. So that's the first step. So complete circle with curve vertex. But now if we want the noise. Let's add the noise back in. If we have the noise, it's still not going to be matched. You see how the first one and the last one is not going to match. One of my AirPod died. The first and last one is not going to match. And how to make it? And the reason why it doesn't match is because now if I draw, let me remove the annotate, clear. That's because, okay, thank you for letting me know. As I mentioned, yeah, feel free to go, but this will take a little longer, and you can come back and watch the recording. So the noise looks like something like this. And what we are doing here by using the eye, essentially we are just selecting a section of this. That's why the first one and last one, there's no guaranteeing that they're going to match. There's basically no way that you can make sure they will match. And then maybe you are selecting another section, the first one and last one, they're not the same radius. But how do we work around it? That we need to go back to this grid thing. We need to use 2D noise. So instead of selecting the noise on one axis, which we can't make sure the first one and last one match, we can select the noise in a circle. That way we know this is the first noise value we get, and maybe a couple more. And when you go back, the first and last are both here, or very close. And in this noise space, because of the way the noise is designed, when the two values are very close to each other, they're going to be a smooth transition. And because of that, instead of I, we're going to access it via, with a circle. And how is it going to be a circle? Then that's when we're going to use sines and cosine again. So it's going to be sines I and cosine I. Let's focus on this first. I think this is getting a little too long. So one way we can break, let me undo. One way we can make it simpler is to create a new variable. So for each curve vertex, instead of radius, we want to use a sort of calculated radius. That's calculated with noise, calculated radius. So I'm going to replace these two and copy this. I'm going to replace these two. Let's see. Yeah, then there's no error. So calculated radius, let's say for now it's the same as radius, so it's circle. So how do we want to calculate it? We want sines times noise function. And instead of the I, we're going to add two inputs. One is sine, the other one is sines I, the other one is cosine I. I'm going to break this into two lines, sine I and cosine I. And now, in order to get the perfect circle, essentially we need the same thing here. Instead of I, we want it to be I divided by number and times 2 pi. So I'm going to copy the same thing here. then there was the extra comma. That means it's missing a parenthesis here. It's really getting, no, yeah, there we go. So sine and cosine. And that's essentially is accessing, that's the coordinate for a circle. If we look back, now it's complete. Even if, let's say, if I remove coming out to noise speed, it's always going to be complete. But now we have another issue, and that issue is it's symmetrical. And it's symmetrical, that's because that's how noise works. The way the noise space works is that around the axis, this part and this part is symmetrical. And this is also symmetrical. And that's the reason. So what we were doing earlier with this circle, sine and cosine is to access the noise space around the origin. So this part and this part is going to be symmetrical. So instead of around the origin, we want to access the noise value only in one section. Let's say just the top, only in positive space. So we can simply add 1 to both sine and cosine. That way there's no symmetry. And if that sounds like too complicated to understand, basically if you want to avoid symmetry, just make sure the input is always larger than 0. It's always positive. That way there's no symmetry. And because the minimum value for sine is -1, so if I added with 1, then it's never going to be negative, and that avoid the symmetry. So this is very close to what we're looking for. Just make sure the code, yeah, that all looks good. And now we have the noise. We have the blob. Finally, if you want this to move, you are going to add one last input or access, which is going to be frame count divided by a number. Now there you go. Now we have a blob that moves with noise function. So cool. Blob based on noise, and another one. This one is animated with noise. Yeah. And now you can adjust different features. You can make the radius a little bit bigger, and you can use a noise seed to make sure that every time you refresh, it's the same noise. There's all that different thing that you can do. And in addition, I have in the code collection that I've shared, you'll find for the workshop number 3, there's 2 demos. One of the demo, I think I might have forgot to add it. Let me add it right now. Blob with noise. I'm not sure why it was not added. If I refresh, you'll see at the bottom there's a blob with noise. This you can try, this is something you can test with, like you can adjust the number of vertices, and then the base radius, And then there's also two other things you can adjust. That's called level of details and fall off. So this is how you can adjust the characteristics of the noise. And again, if we go back to P5 as reference, there's something called noise detail. This gives you a little bit of control over how you want the noise to look like. And if you're interested in that, you can look at you can read the description here of how you can adjust it. It's a function called noise detail that takes two inputs, and based on two inputs, the noise will behave a little bit differently. And that's one. And then there's another one. All the way to the bottom. There's another one that's 3D noise, where you can adjust the size, the level of detail, and see how the level of detail affect the noise and fall off. Change it to different things. This is like different angle of a pie and the rotation. Yeah, just to test it out. Any questions? I know today, I think with noise, it's a little more advanced topic, and there was a lot to cover. We used noise in 3 different scenarios in this repetition, repeated circles, and then we used it in a grid, and finally we created a blob. So there was a lot of information. So let me know if you have any questions. Yes, exactly. I think really you just need to practice. The more you do, the better you will be at it. You will be at this, and the better you will understand this as well. Loving noise. Yes, exactly. It's really, even though usually when you think about coding, it's usually like very, in a way, it's somewhat rigid, where it have to follow the exact same path. You think about those straight lines, but with noise, the sketch really comes to life in like so really thanks to Cam Perlin for creating this algorithm. And so for today, if there's no question, I'll talk a little bit about the homework. I think for today, you can really just, similar to yesterday, you can pick any topic that we've learned, 3 type of noise that we've done, and try to do something that's different. I mean, if you don't have time, it's totally okay. If you just adjust a couple of numbers, that way you can also learn a lot. But otherwise, try to think about something that with the stuff that we've learned, try to come up with something that uses noise that's different from visually or conceptually, that's different from what we covered in the workshop. And as always, I hope to be inspired by your sketches. I'd love to see your sketches. So please post them on Instagram or send it to me by email. And again, thank you all. Thank you for coming to the workshop. I'll see you tomorrow for the 4th workshop.